Alright guys, so let's talk about section 9.2, which is called using general angles and radian measure. So we want to do today drawing angles in standard position, finding coterminal angles, converting between radians and degrees, which becomes very, very important, and then solving problems involving circles using arc length and area of a sector. Okay, and so first of all, let's talk about angles in standard position. So we're moving away from just our traditional, hopefully you've memorized this now, 30, 60, 90 triangle, which is 1 root 3, 2. And the other one, which is 45 degrees, 45 degrees, and that's 1, 1 root 2. We're moving past this, just these small little acute angles, and saying we need to consider angles anywhere in the plane, okay, that can be even bigger than 360 degrees. So I'll read this to you. It says, in a coordinate plane, an angle can be formed by fixing one ray. So you know that an angle is formed by two rays like this, okay, and we were calling this theta earlier. And so an angle can be formed by fixing one ray. So this is the first ray we're fixing, okay, and we call that the initial side, and then rotating the other ray. So it's like taking this ray and rotating it, okay, around the origin, and then the other ray, wherever you stop, that ray is called the terminal side, and wherever you stop, that will determine how big the angle is, okay. And so an angle in standard position in the coordinate plane has an initial side, always starting at 0 degrees, and a terminal side, and then wherever the terminal side is placed, that determines the size of the angle. Let's say it's theta in the coordinate plane, okay. And an angle is in standard position if its vertex is the origin, which for us, this is all our angles we'll be drawing will be in standard position. Okay, so that's basically just a little definition, so we're all on the same page when we talk about angles in standard position. And then a measure of an angle is positive if the rotation of the terminal side is counterclockwise. So in other words, if I start here, if this is my initial side, let me go to a different color. If this is my initial side, and then I rotate counterclockwise and I draw my terminal side here, whatever this angle is, okay, let's call it beta, whatever it is, okay, it's going to be a positive angle because I rotated counterclockwise. All right, and then if I rotate clockwise, so let me pick a different color yet. Here we go. If this is my initial side, okay, and I rotate from the initial side counterclockwise, and that's my terminal side, then this angle, whatever this is, let's say alpha equals something, is going to be a negative angle because my rotation from the initial side was in the clockwise direction, okay. So if I rotate counterclockwise, the angle is positive. If I rotate clockwise, the angle is negative, okay. That's all that little blurb there means, all right? And that doesn't feel right because it feels right that you go this way and it should be positive, but that's not how it works, okay? So clockwise is negative, counterclockwise is positive, all right? So the example here is, example 1 says draw the angle with the given measure in standard position, okay. Draw this in standard position. And so what you do is and also please remember that this is maybe new for you, maybe, I'm not sure, but 0 degrees is here, and then if I've rotated all the way around, 360 degrees is also there, okay. And for every revolution you go around, you add another 360 degrees here. So if I go around twice, this would be 720 degrees, okay? And then 90 degrees is here, 180 and 270. That's also quite important, and I don't want to take for granted that you know that. All right, so draw an angle in standard position. So you just draw your coordinate plane. Okay, and then I'll do it in a different color, and let's say we draw the initial side. Okay, so this would be my initial side, and you don't have to do all this. I'm just doing this just as an introduction to you, and then rotate around 240 degrees. So 0 degrees, I'm starting here. Okay, so if I'm now taking my terminal side and I'm rotating it, so here was my terminal side and I'm rotating it. Okay, I have to go past 90 degrees because my angle I have to draw is 240 degrees, and so I have to keep rotating, and then I have to go past 180 degrees because I'm looking for an angle that's 240 degrees. Now 270 degrees is here, and so therefore I'm not rotating all the way to 270. Somewhere over here will be my terminal side. Okay, so this will be my terminal side, and then we can say that this angle here is 240 degrees. Okay, it's kind of hard to label your angle because it looks like I'm saying this is 240 degrees, but obviously I'm not. Okay, the whole angle is 240 degrees. All right, so something like that. And please, you don't have to label all these things. I'm just doing it so that you understand what's going on. What you should be drawing is probably just, this would be sufficient to show that you understand what's going on. Okay, just right there, 240 degrees. You have an understanding of what's going on in the coordinate plane. All right, okay, so then 500 degrees, that's a bit of a different situation. So again, and notice we went counterclockwise to here because we want a positive angle. Okay, negative would go clockwise. So 500 degrees, I'm gonna go a little bit faster here. 0 degrees is here, 90 degrees is here, 180 degrees is here, 270 degrees is there, 360 is here. Oh, but our angle is bigger. So if I go and if I add from here to here another 90 degrees to 360, what am I getting? Maybe 450 degrees. And then if I add another 90 degrees from 450 and I go all the way here, that would put me actually at 540 degrees. So we can see that our 500 degree angle should be here somewhere. Okay, and so how does that work? Well, you fix your initial side. Here's my initial side. Okay, and then I start rotating. So I'm rotating my terminal side right now. 90, 180, 270, 360, but that's too small. Keep going. 450, and then I need to get to 500. Now 450 will be plus another 50 degrees. Okay, and so there, 450 plus another 50 will give me my 500. So here will be my 500 degrees somewhere here, but not quite yet here because that would be 540 degrees. Okay, so just 500 degrees. So there's your 500 degree angle. Okay, and this is my initial side. This is my initial side, and this would be my terminal side. Okay. All right, so that's positive angles rotating counterclockwise, and then negative angles rotating clockwise. All right. Here is my coordinate plane. And let me pick a different color. So my initial side would be here, and we're at 0 degrees right now, but if I'm going clockwise, then we get negative 90 over here, negative 180 over here, negative 270 over here, and negative 360 over here. So if I'm starting here and going clockwise, then I go just down here to negative 50 degrees. Okay. All right, and then negative 300 degrees. Again, very, very similar idea. So draw your coordinate plane, and then start here. This is 0 degrees, negative 90 degrees, negative 180, negative 270, and negative 360. So I know that I don't have to go all the way to negative 360. Sorry. And so I start here, and I do this. I go there. Here's my initial side. My angles are negative, so I'm going clockwise, and I go all the way to here. And that's that. And so that what I have here is this angle all the way around is negative 300 degrees. Okay? And so that's how to draw an angle in standard position. They're all standard position because the vertex, which is right here, is at the origin. Okay? And then coterminal angles. Coterminal angles are defined as angles which have their terminal sides coinciding. Okay, so the initial side is always at 0 degrees for positive or negative angles, but coterminal angles are angles that have their terminal side in the same place. All right, and so angles that end in the same place but they're different sizes basically is what this means. So angles that end in the same place but they're different sizes. Okay, and so how that works is you can do it this way by just adding things. I'll show you a visual of what a coterminal angle is. Okay, but you can find coterminal angles just by multiplying or subtracting multiples of 360. But let me show you a picture of what this means. If, let's say, let me draw the angle negative 45 degrees. So here's 0 degrees and here's negative 90 degrees. Okay, so the initial side is here. Okay, this is my initial side, and then my terminal side for the angle negative 45 degrees is exactly halfway down here. Okay, this would be negative 45 degrees, and this would be my terminal side. All right. Well, coterminal means their terminal sides are the same, okay, but it's a different angle. So I'm going to do this in green. Let's say my initial side for my green angle is also here at 0 degrees, but I want to find a positive and a negative angle that's coterminal with negative 45, okay? So what I can do is say, oh, if I start here at my green initial side and I rotate counterclockwise around and I get here and I call this my green terminal side. Okay, notice their initial side and their terminal side are the same. Okay, and then this angle, how big is this angle? Well, I went the positive way around this time. So this is 90 degrees, this is 180 degrees, this is 270 degrees, and this would be 360 degrees, but I didn't quite get to 360. I stopped 45 degrees short of 360. Okay, so it would be 360 minus 45, so this angle would be 315 degrees. Okay, so that would be a positive coterminal angle. Now what they told you is you can just say for the positive coterminal angle, you just do this, negative 45 degrees, and it says to find your coterminal angle, you can just add or subtract multiples of 360. So if I add 360, I just get 315 degrees, but that's what we drew. Okay, and then to get my negative coterminal angle, they say you can just subtract 360. So if I take negative 45 degrees and I subtract 360 degrees, I just get negative 405 degrees. Okay, but again, you can draw that if you really want to. You can have a visual representation of how this works. And let me erase some of this stuff carefully here. Hopefully I don't destroy my whole picture. Can I do it? Oh, I think I did it. Okay. And let's go to a different color. Let's say blue. And let's say my initial side is here. My blue initial side is here. And now I'm going to do a negative coterminal angle. So I have to go also this way in the negative direction. But I can't stop here because that's just negative 45 degrees. So I have to rotate all the way around and come all the way over here. Okay. So what I did is I went in the negative direction all the way to 360. So this is negative 360 for my blue angle. And then I went another 45 degrees in the negative direction. Okay. And so that means that this blue angle here, that's got the same coterminal angle, coterminal side, or terminal side, sorry, and it's also a negative angle, would be negative 405 degrees. Okay. And so that's a visual representation. Most students don't want to do this. You just want to add and subtract and do it algebraically. But there's a visual interpretation for you of how this works. All right. So all you can do to find a coterminal angle is just add 360 if you want to find a positive coterminal angle, or subtract 360 if you want to find a negative coterminal angle. So if you look at this, let's say I want to find the positive coterminal angle. You say 395 plus 360, and that is just 755 degrees. All right, so there's a positive coterminal angle. I don't have to draw the picture, but you could if you wanted to. And then a negative coterminal angle. Now here you'll see an interesting thing. If I do 395 minus 360, I don't actually get a negative angle. I get a positive angle still, because my initial angle is bigger than 360. So what you got to do then to find a negative coterminal angle is just subtract another 360. So you just say 35 degrees minus another 360. In other words, just go around once more. Okay, and then what you get here would be negative 325 degrees if you do that on your calculator. Okay? All right. And I'll let you mess with this example C. Same thing, add or subtract, continue adding and subtracting until you get a positive or a negative coterminal angle. All right? Okay, so let's talk about this. The next topic here is not students' favorites one generally, okay? And that is radian measure. So let me first just say this. You might think to yourself after I talk about this, why in the heck are we doing this? It just turns out it's hard for me to justify this for you with the kind of math that we're doing right now. But suffice it to say that engineers and people who use calculus a lot use a different angle system. They don't use degrees, so we call this little symbol degrees. They don't use degrees. They use radians. Okay, and it just so happens that doing calculus and engineering and some of the more complex math that you would likely never see in your life relies on using radians as your angle measure. Okay, and so then you say, what is a radian? All right. So a radian is defined this way right here, but this is not, I don't think this really helps you understand what a radian is. I have a little animation I'll show you in a second, but a radian basically is an angle that's formed by rotating the terminal side until you have drawn an arc that's the same length as the radius. Okay? And that angle here would be called 1 radian. Okay, and so 360 degrees. So we said if this is 0 degrees and I go all the way around, we said that's 360 degrees. And you just saw the animation there. That is the same as 2 pi radians. Okay, or 6 point something, just over 6 radians. All right. And then same thing here, you know that this is 180 degrees, okay, and that's a radian. If I go just a little bit over 3 radians, we call that pi radians because it's 3.14 radians, okay, and so this is pi radians, all right, and so we just eventually start labeling this 0 and this pi over 2 and this pi. So 90 is half of 180, so this must be half of pi, so pi over 2. And then this is 3 pi over 2, and then this is 2 pi. Okay? And so that's something that you have to become very familiar with. Now, two things. One is, how can I easily convert between radians and degrees? And there's a formula for this. I'll show this to you, but you need to be better than this. You need to be faster than this. So in calculus and pre-calculus, and for the rest of this year in trigonometry, you're going to have to be able to convert angles, commonly used ones, not esoteric strange ones, but commonly used angles. You're going to have to be able to convert them between radians and degrees fairly quickly. Okay? And so I'll give you the formula, but unfortunately for you, you're going to have to either understand this or memorize it. Now, I don't recommend memorizing it. I recommend understanding how can I quickly convert a radian angle to degrees so I can visualize in my mind how big it is, or just work directly in radians and you don't have to even convert them, just understand where they are in the coordinate plane. Okay, so this is super important. If you don't know how to quickly convert degrees to radians and vice versa, then you are going to be really stuck when we start doing our other trigonometry. Okay, so please understand this, and if you can, and I'll show you some strategies for this. If you can understand it, memorize it. All right, I think everybody can understand it, how to convert, but you know, if you don't want to take that time, you want to memorize stuff, then just memorize it. Okay, so what we have here is two little formulas. If I want to convert from degrees to radians, there's a formula. So you multiply the degree measure by pi over 180, and what will happen is you're dividing degrees by degrees, so the degrees cancel and you end up with radians. Okay, so I'll show you how that works. If you want to convert this degree to radians, you use this formula, okay, degrees to radians, and I just say multiply by pi radians over 180 degrees, and now you get something that you have to basically reduce. So you get this 125. Now please notice the degrees cancel. Okay, if you're into unit conversions and stuff from like physics or something, and you get 125 pi. You can write pi radians, but we all understand that pi means radians, over 180. And actually this is done, but you just have to reduce. So what can I divide them both by to reduce this? And the answer is just divide top and bottom by 5, and you get, this is a pretty esoteric, strange angle. Okay, 25 over 36 pi. We don't often work with stuff like this, but you should know how to convert any angle from degrees into radians. So just, if I want to convert from degrees to radians, just multiply by pi over 180 degrees, and then just reduce and simplify. Okay, so how can I reduce this one? Well, I can divide, the degrees cancel first of all, so what I'm going to have left is pi radians, okay, something pi radians, and then just divide by 10, and so I get negative 50 divided by 10 is 5, 180 divided by 10 is 18, and you can't do anything else there. So again, very esoteric little angle here, not something that you find on this unit circle there, but yeah, okay, at least you can do it. And then going the other way, again, think I want the pi to cancel out, so I put 180 degrees over pi, and then the pi's cancel out. Okay, and so that's how you can remember which formula to use. And then you're going to get negative, and reduce this again. So 12 can divide by itself once, and 180 divides by 12 15 times. Okay, 15 times. So everything cancels, what's left is negative 15 degrees. Okay, the degree did not cancel because there's no other degree to divide it out. Okay, and then here, same thing, multiply by, again, I want the pi radians to cancel, so I multiply by 180 over pi. This will cancel, I'll have degrees left, and then just reduce and simplify. So what you get here is 4 goes into 180, 45 degrees, what's left there. So 5 times 45 degrees, you just get 225 degrees. This is not a strange angle. This is something you should become very familiar with. 5 pi over 4, if you look over here, 5 pi over 4 is an angle we use a lot. Okay, so that's something you're going to have to eventually understand without having to memorize or whatever. All right, and so let's move on and get into some actual problem solving. So I'm going to go over this with you real quick and give you some strategy, or a strategy, for how to understand all these angle measures. So what you have here is a diagram that shows you how to convert degrees and radians for commonly used angles. We use these angles a lot. And you can see why, because we know corresponding triangle information for and trigonometric ratios for these angles. Well, where do these angles come from? 30, 60, 90. Oh, that's a triangle, 30, 60, 90. And then 45 and 90. Oh, that's another triangle that we've memorized. Okay, so basically all of your trigonometry ends up depending on those angles and your ability to do quick calculations with those angles. Okay, but this is not 30 degrees or 60 degrees or something like that, but you'll see later that they're actually very closely related. Okay, we call them, you can use a reference angle in here, and the reference angle here is 60 degrees, something you're going to see later. So they're very, very closely related to these. So the base few little angles that you memorize your triangles for, all these other angles that we commonly use are very closely related to those angles by reference angles. Okay, and you'll see that later. So, question. This you've got to just get in your head. Okay, the basic 3 just got to memorize, or the basic, let's say 4, and that is that pi over 6 means basically 180 degrees divided by 6, which is 30 degrees. That's why pi over 6 is called 30 degrees. Okay, and then pi over 4 is 180 degrees over 4, and that gives me 45 degrees. Okay, that makes sense. And then pi over 3 is just 180 over 3, which is why we call pi over 3 60 degrees. Okay, so 0 degrees is 0 pi radians. Okay, 90 degrees is pi over 2 radians. We had that earlier. 180 degrees is pi radians. The animation showed you that. And then 3 pi over 2 would be 270 degrees. Now, how can I understand that? Okay, so this is 0 pi over 2, 2 pi over 2 is here, 3 pi over 2 is here. Okay, but we know that this is 270 degrees from our degree coordinate plane, so then the radians would be 3 pi over 2. Okay, and the animation showed you in radians that 2 pi is equal to 360 degrees. So that's okay. So then how do I deal with all the other weird ones? Okay, so this you got to have in your head. Pi over 6 is 30 degrees, pi over 4 is 45 degrees, pi over 3 is 60 degrees, and pi over 2 is 90 degrees. Okay, how do I deal with the other ones? So let me take all this stuff out of here, and it's how do I deal with the other ones? So what you say to yourself is this. Let's pretend you don't see this. Let's pretend you don't see this, and I ask you, hey, how big is 2 pi over 3? Or you'll later learn what's the reference angle or something like that. Okay, so what you say to yourself is this. Well, 2 pi over 3 is almost pi. But how far do I have to go to get to pi? Okay, I have to add another pi over 3 here to get to pi. So I am pi over 3 away from pi. Well, what's pi over 3? 60 degrees. So I'm 60 degrees less than 180. Well, 60 degrees less than 180, if you erase all this, you'll see is 120. Okay, so that's a good strategy for you to figure out how to remember this stuff. How far do I still have to go from 2 pi over 3 to get to pi, to get to 180? That is, I have to add another 60. That means that if 180 minus 60 is my 120. Okay. Another angle, let's try another one. 3 pi over 4. How far do I have to go to get here? Well, 3 pi over 4. I need to add another pi over 4 to get to 4 pi over 4, which is pi. Okay. So I need to add another 45 degrees. So this angle is 45 degrees less than 180. So 45 degrees less than 180 is 135. All right. And that's basically how you can memorize all of these angles. Let's see a different one. Let's say I'm at 7 pi over 4. Okay. Well, okay, 7 pi over 4. How far do I have to go to get to 2 pi? That's the question. Okay. So you're always asking yourself, how far do I have to go to get to the horizontal axis, or how far past the horizontal axis am I? All right. So 7 pi over 4. If I added another pi over 4 here, then I would be at 8 pi over 4, which is 2 pi. So I know pi over 4 is 45 degrees, so I'm 45 degrees less than 360, so that's 315. Okay? And that's the kind of thinking you have to be able to quickly convert between degrees and radians. Again, please trust me, if you can't convert quickly between degrees and radians, life will become pretty challenging. All right, I can't do anything else here. I'm gonna leave it there. You either memorize this whole thing, which I don't suggest, or make those relationships and connections for yourself in your head. Okay, figure out how can I quickly go. If I just said to you, if I took this away and didn't give you the crutch, and I said, hey, what is 5 pi over 4? You say, oh, it's 45 degrees more than 180, must be 225. Okay. You shouldn't have to think about that for very long. All right, so that's that, and we'll use that in a second. But then there's two things here. I'm not going to do this with you because I want to make this video shorter. But usually in class and when we're rolling and having a good time, I added this. Your textbook doesn't have this. This is an added, not a proof, but like a little derivation, just like a little example explanation of where does the arc length formula come from. Okay, where does the arc length of a sector of a circle? So arc length means this distance here. Okay, that's an arc, and so the arc length of a sector, this is a sector of a circle, a slice of a circle, like a slice of pizza. Okay, how can I calculate the arc length? If I know the radius and the angle that's formed by that arc. Okay, and the answer is, there's the formula. All right, I'll let you go read this. I don't want to go over the whole proof here because the video is already going to be way long. All right, so read this little derivation. It's not really a proof, and then you should hopefully you understand why the arc length of a circle formula is pi times r. And then if you understand that, then it's very simple to go from there and say, why is the area of a circle, of a sector of a circle, pi r squared over 2. Okay, pi r squared over 2. Not pi r squared over 2. Theta r squared over 2. Okay, I'm reading it right here. Theta squared over 2. Okay, theta r squared over 2. All right, so please go read that. It's useful, but I don't want to do the whole explanation with you right now because the video, like I said, is already way long. Okay. All right, so then here's the formula that your textbook gave you. All right. If this is my sector of my circle and this is the arc length, all I need to know to find the arc length is to say what's the radius of the circle and what is the angle formed by that sector. Okay, and then to find the area, all I need to know again is what's the radius and what's the angle formed by that sector. Okay, so these two formulas you should know. I can't remember if they're given to you on the test. I will confirm that with you later, but this is something you should probably know. Okay, like, you know, the area of a circle is pi r squared, and you know that this circumference of a circle is 2 pi r. So this is another two formulas that you probably should know. Okay, going forward. So there's that. Let's and the central angle. Sorry, I'm going through this very quickly. The central angle is the angle here that's formed by the two. The initial side and the terminal side, that's the central angle of the sector of the circle. Okay, of the sector of the circle. All right, so let's actually apply this. It says a softball field forms a sector with the dimensions shown. Find the length of the fence. Okay, so find the length of this fence. All right. And this might seem to you like a stupid example, but actually this is totally not stupid example, right? You could very easily say, I want to make a little softball field with that size, but then you have to ask yourself, how much fencing do I need? And you don't have time to go back to the store 3-4 times and latch a bunch of stuff together. You just want this exact amount of fencing. Maybe you'll have a little bit more, but you don't want to have too little, okay? And so all you have to do then is say, oh, here's the central angle, which is 90 degrees in this case, okay? And so I have, if it says find the length of the fence, well, the length of the fence, that would be the arc length, okay? So this means arc length here, and then find the area of the field. Area of the field, again, would be very, very important if you want to order like grass, pre-made square grass patches to plant the field, okay? So the area. All right, and so what you have to do is just say, well, let me write arc length would be equals to the length of the fence, okay, which would be, and then you just plug stuff in. So the arc length is the radius times theta, okay, which is the central angle. And if you do that, you get the radius is 180 feet, okay, times the angle, the central angle here is 90 degrees, okay. And then what you get is, and actually, sorry, I have to clarify this. Please, this formula uses radians. It uses radians, not degrees. It uses radians. I just made a critical mistake there. It uses radians. So 90 degrees is pi over 2 radians. Okay, so you plug in pi over 2. But now this is tricky. Please pay close attention to this. What happens at this point is you get 180 times pi over 2. So this cancels. You get 90. So 90 times pi feet, okay, is what you get. But at this point, the pi does not mean, don't write degrees in here. At this point, pi radians actually means this, 90 times pi as in 3.14 or so on feet. Okay, so when you go on your calculator and type this in, you do 90 times approximately 3.14, whatever you could type the actual pi constant on your calculator, and then you get, I think you get about 282.6 feet. Okay, so please, many students don't pay attention to this. Many students remember to convert 90 degrees to pi over 2, but then when they get to the answer, they want to write something in terms of degrees or something weird. No. The pi turns into the constant or the number pi 3.14. So let me see if you actually enter this in your calculator, what you get. If you enter 90 times constant pi, yeah, about 282.74. What did I have? 282.6 because I used the 3.14 rounding. Okay, so please, that's what we mean by pi in this case. The pi turns from an angle measure to the constant 3.14. That's a bit tricky, okay? And then the other example is the area, okay? And again, area here, theta, the angle is measured in radians, so we'll do half the radius squared, which the radius is 180 squared, times the angle, which is 90 degrees, which is pi over 2. Okay, and if you do that calculation, you get about 8100 pi. And again, this means basically 3.14. So on your calculator, you'll type 8100 times pi like this. Okay, and you'll get about 25,446.9 square feet. Okay, so 25,000, sorry, what did I say? 446, 446, 0.9 square feet. So if you were buying stuff at a store, you'd probably just go 25,447 square feet, something like that. And you'd probably actually honestly buy a little bit more than that. But okay, at least you have a very accurate idea of how much grass you would need to cover that field. All right. And then this is an interesting example. I think example 5. Example 5 is pretty long example. I don't think I'm going to do all of the parts of this. I think maybe what I'll do is find the area of the entire sector and then maybe the double region, and you can figure out how to do the triple region from our completed note sheet. Okay, and so here's a dartboard, and they're saying it's divided into 20 sectors. Okay, so there's a sector of the dartboard. So if you look carefully here, they took one of these sectors and blew it up. Okay, they took one of these sectors and just blew it up, and it looks like that. Okay, so there's 20 of them in here. 20 of them in here. Okay, and so from that, the number 20 is significant. From that, you're supposed to be able to figure something out. And then it says each sector is worth a point value from 1 to 20. Okay, and has shaded regions that double or triple this value. A sector is shown at right. Okay. So if you've played darts, maybe this makes sense. If you haven't played darts, maybe it doesn't make sense, but that's okay. All right. And it says find the area of the entire sector. So we're looking at this formula. Area of a circle, or area of a sector of a circle is half r squared theta. Okay. Half r squared theta from up here, where theta is radian measure. Okay, so the entire sector, find the area of the whole thing. That's the question. All right. Okay, so what you do is you say, how do I find that? Well, what I need to know is this central angle. I need to know the theta, and I need to know the radius of the whole sector. But that's okay, they gave me the radius. Okay. So you just convert that to maybe a proper fraction, and then, but we have to find the central angle. But now they gave you some information. There's 20 sectors. Okay, so you know that the radians or the degrees in a circle is 360 degrees, but we're working in radians, so that's 2 pi radians. Okay, and then I'll have to divide that by 20 to find my central angle, because there's 20 sectors in the circle. Okay, so all I have to say is, oh, this is the whole circle. Okay, so this is the whole circle. I have to divide that by 20. So the whole circle divided by 20 will give me the central angle of a sector. Okay, the central angle of a sector. Okay, so in other words, take the whole thing and split it into the 20 pieces they told you, and then you get the central angle. So what is that? So 2 pi is the whole circle in radians divided by 20. So if you do that, you get pi over 10. Okay, so the central angle is pi over 10. So we did it. The central angle here is pi over 10. Okay, that's the central angle. And so now I can find the area. Let's say we want to find the area of the entire sector. The entire sector. How do I do that? I do this 1/2 times the radius. Now here's the radius, 6 5/8 inches. So you need to convert that to a proper fraction. Okay, so 6 times 8, 48 plus 5, 6. What's that? 53. So 53 over 8. So 53. 53 over 8 inches. squared times the central angle, which we said is pi over 10. Okay, pi over 10. And if you do that, you get, it's going to be approximate because of pi, but you get a number. So let's type that in and see what we get. Okay, so we do 1/2 times 53 over 8 squared, okay, times, and now pi over 10, you use this pi right here, okay, pi over 10. Let's see what we get. Okay, and what you get is about 6.894. Let's round to the thousandth. Okay, 6.894 inches squared. Okay, because I squared my inches right here, so inches squared. All right, 6.894 inches squared. That's the entire sector. All right, that's fine. Let me erase some of the scratch here that we no longer need, and say, all right, now here's the next question, and then I'll stop. Okay, it says a double region. So find the area of the double region. Ooh, this is a bit more tricky. Okay, so the double region is just this little thing here. All right, just that little thing. How can you do that? Think about it. Pause the video, think about it, try and do it yourself. Don't let me do everything for you. Okay, if you figured it out, you can check if you did what I did. There's probably other ways, but one way is to do this. Say, okay, if I can take the whole sector, okay, and then I subtract this piece that excludes the double region, then the whole sector minus the piece excluding the double sector would give me the area of the double region. Okay, so that's what we're going to do. We're going to say take the area of the entire sector, okay, and subtract from that, let's see, what do I call it, the area without, the area of the sector without the double region. Okay, the area of the sector without the double region. Okay, so I'm taking the whole thing, and then I'm saying take away from that the red part, and then what's left? Only the green part is left. So that's how I get that. Okay, so let's do that. So let's say, what's the area of the entire sector? Well, we said that's 6.894 inches squared. Okay, minus, and then I have to find this. Now this is annoying, but that's not too bad, because the entire sector's radius, we said, is 53 over 8 inches. But then I'm taking away 3 over 8 inches. Okay, so the red region, let me write that in red, the red region of the sector without the double region is just 50 over 8 inches. That's the radius for this sector right here. Okay, it's the 53 over 8 minus the 3 over 8. Okay, so what you do is, to find that area is just 1/2, and the radius is 50 over 8 squared, times the central angle is the same. Okay, the central angle is still pi over 10. And so I think if you do that calculation, you should get your answer. So let's go back here. What do we have? We still have that in there, minus, and then just do like a parenthesis and say another parenthesis, minus 1/2 times 50 over 3, 50 over 8. I don't know why I keep saying 3. 50 over 8 squared times pi over 10. And see what you get. And so I think that's correct. That's correct. Okay, so what you get is 0.758. Right, so 0.758 square inches. Okay, inches squared. So what we just said is that, let me erase all the scratch here. We just said that the area here, and I don't know how to draw this so you can see it because it's not really coming through well. This right here, okay, that area there is 0. What do we say? 758 inches. 758 inches squared. Okay, that's that. Alright guys, that's that for that problem. There's another one that's even more challenging. Find the area of the triple region, but I'll let you mess with that. It's also on the completed note sheet. Okay, and then it says, part B says, a dart you throw randomly lands somewhere inside the sector. What's the probability that it lands in the double region? Now this is something that you really should have done in geometry class. I'm not sure if you did, but there's something called geometric probability. Okay, so it's a question about probability. And now we're talking about geometry because we're talking about shapes and things. So this is a geometric probability question. Okay, and how geometric probability works is you take the area that you want to know what's the chance that you hit that area or that your dart lands in that area divided by the total area. Okay, and so what you say is the geometric probability here is the area in question, so the area of the double region, which we just found, okay, over the total area of the dartboard. Okay, sorry. The area of the circle, the sector. Okay, so the area of the sector, not the total area of the dartboard, because the prompt said a dart you throw randomly lands somewhere in the sector. So the total option for my dart to land somewhere is anywhere in that sector. Okay, so what's the chance that it lands in this double region right here? That's the question. Okay, and so you say the area of the double region divide by the area of the total sector. You know it's landing in the sector, but what's the chance it lands in the double region? And now, fortunately, we've already done all the calculations here. It's about 0.758 inches squared is what we said, over, and this was inches squared, over about 6.894 inches squared. Okay, and then you get some approximation to an answer. Let's see what you get. So you say this answer we just had, 0.758 divided by about 6.894, and you get a probability, which, remember, probability must be less than or equal to 1 and bigger or equal to 0. Okay, and so 0.109, if you round that, you get about 0.11. So about 0.11, that's the probability. So again, what does that say? If I throw a dart and I know that it's going to land in this sector, okay, in a sector, what's the chance that it lands here? 11% chance that if I know my dart's going to hit somewhere in this sector, that it hits in the double region. Okay, and then the last thing here, I really want to finish this video. I apologize that it's 14 hours long. Is practice doing your finding trigonometric ratios of angles that are in radians. Okay, so now you should know this one by now. Let's see if you know. What is pi over 4 radians in degrees? How would I do that? Okay, and so you can say, this is the same as sine of 45 degrees. And so pi over 4, it's the same as sine of 45 degrees. Now our hope is that you don't have to do this, convert to degrees, that you understand it. But we only have a triangle for this, 45 degrees, 1, 1, root 2. So sine is opposite over hypotenuse, right? So sine is 1 over root 2. And then you can't leave it like that. You must rationalize, so you get root 2 over 2. Okay? So hopefully you can go straight from here to here and you don't have to write this. Pi over 4 means 45 degrees, so I'm doing a 45 degree triangle. That's what you should be thinking. Okay? This one, on the other hand, pi over 9, I don't have some kind of a reference angle or understanding of what pi over 9 is. We don't have anything like that. That's not anywhere on our little list of commonly used radian measure angles. Okay, so when you see something like that you don't recognize, pi over 9, you're probably going to resort to using your calculator. 6, I guess, if you round to the thousandth. Okay, 1.346. Please don't worry too much about the rounding. Round to the hundredth, round to the thousandth. I think rounding to the hundredth at this point is at least what you should be doing. Rounding to the 10th might make your stuff inaccurate. Alright guys, I hope that really helps you for the section. Pretty long section. Please, lots of things to practice. Make very, very sure that you get this thing down. Okay, you got to have that in your head going forward. Otherwise your quiz and test is going to be a disaster. Alright guys, thank you.